So today I'm going to talk about the DSS, the open source peta and terabyte scale storage engine for high bandwidth application. So this is a joint effort in our team in MSL Solution Lab at Samsung, which is the Memory Solution Labs with my teammates. So today I'm going to talk about the motivation and the introduction behind the solution that we provide, this storage solution that we provide, and what is the architecture behind it. And we compare it with some common solution, and then we will conclude our presentation. So as we know, the exponential data generation in different big data applications such as IoT, AI, security, deep learning, all these are generating a large amount of data, but we cannot just let this data out. We need to process them. We need to extract information and value from them. So, but mining this amount of data is not really easy. So the large amount of data, most of these large amount of data are generated unstructured, and it's mostly in object format. So the regular solution like data lakes or locally attached storage or traditional network storage, data storage, it's really have this inherent scaling and performance bottleneck problem. So our Samsung DSS or storage solution for petabyte data is actually serve the AI or deep learning application or all these applications who has got the read intensive and with disaggregated high bandwidth and easily scaled object storage format. So then as we were talking, this petabyte data is not really easy to manage. So we should come up with specific solution for them that it's not really concerning the IOPS, because the IOPS is just reading like small amount, like reading the data is small, but when it comes to petabyte, each time you're reading, it's a lot. So we should focus more on the bandwidth and the scaling of the bandwidth. So our goal is to achieve the highest bandwidth performance for existing technology and scale the capacity in order of the 100s of petabytes. The main focus of our architecture is for the high bandwidth reads scaling. So we kind of deprioritize the write in this one, but we want to read for terabytes per second for AI, ML, training, and other similar applications. So our DSS disaggregated storage solution implements the object key value API on top of the NVMe over Fabric, and it's designed explicitly for objects, and it supports the remote access protocol and facilitates the disaggregation of the computational and storage, and in this respect, it gives us the scalability. It's also have this global namespace for the object-based storage management, and it will come that it has the ability to move the data from the storage device to the client over the RDMA. Right now, we are just having the data go to the system memory and then to the host. But in future, we will have this, like pretty soon, we will have this, that it goes through the RDMA. So the architectural design behind our solution is that it has three main parts, is that the storage server, our network, and the client side. So the storage side, we have this front end and the back end. So in the front end, you will see the MinIO, which is a well-known Amazon S3 compliant open source object storage, use the KV API to store the data and access the data. We modified the stock MinIO so that it gives us this distributed, shared everything with a better performance and improved performance and scaling. And we are using the erasure coding for data consistency, faulty drives, or random bit flipping. So each S3 object has been sliced into one or more strips, and then it will be coded, the erasure coded across the nodes into the clusters, so that we don't really need any extra redundancy on that node level. So on the storage server, each DSS storage run both the MinIO and the KV NVMe over Fabric in a hyper-converged mode. So this hyper-converged mode it means that we have physically both of them on one server, which gives us the better capacity and density on one resource unit, though the customer can decide on both modes. So the KV value NVMe over Fabric target receives the object and then hash the keys and evenly distribute this over the SSD. The current solution, we are using the RocksDB instance per each SSDs to store the metadata and object into the block SSD. So in future, this will be replaced with the key value SSD of the Samsung technology, which is more context-aware, and would let us to do some near data processing, and in this way it will help us in a better performance too. So the network setup here it basically consists of two layers. One is the front that you will see this HTTP, the S3 HTTP and TCP/IP, and then on the back you will see the Rocky V2. So the Rocky V2, it's for the protocol network for the NVMe over Fabric, the backend to transfer the data between the storage cluster. We decided because if we use the TCP/IP, it has the more CPU load. This DSS, as we talked, is more for the read bandwidth performance in NVMe for more read performance. So the NVMe backend would performing the zero copy data transfer from the PCIe Gen 4. The next step for us is to add the RDMA extension to the S3 protocol. So right now, by using the HTTP S3 over the RDMA, we are eliminating the inherent NFS version for the V4 overhead that inherently is there, by using the S3 and fetching the whole data and the entire object without additional metadata transaction, which is done by NFS. So we are evaluating our architecture using the NFS as a baseline, and then we are comparing it to our DSS storage. So we are using the same hardware, identical data set with 6 homogeneous storage server and 1 to 12 client server. We have evaluated based on the data set of 120 terabytes. On each storage node, we have 20 terabytes of data on each of them. And NFS protocol we're using is XFS, and then this DSS is without RDMA. So the client nodes are running the internally developed AI benchmark that we developed. So this AI benchmark tool is our internal developed tool, which simulates large scales of the data parallel for training the AI and ML workloads. You can generate the data across all these nodes and then initiate your model, and you can decide which platform you want to work on. Is it the PyTorch or is it the TensorFlow? Each client running 2 training session and instance with 50 worker per each instance. So what we would see is that the DSS is easily scaling up into 140 gigabytes bandwidth with only like 6 nodes. With all the 12 nodes. So it also goes up linearly. And then the NFS is just, it's maxed out at 37.7 gigabytes. And so we will see that the DSS is able to get this 3 times scale up, 3 times more performance, and also giving this global namespace support. DSS would reduce all this protocol-related overhead that NFS has. So it gives us the benefit for the performance and the bandwidth that we want to achieve. So in conclusion, the DSS is a major design goal is to achieve the highest bandwidth for the existing technology and scaling to the hundreds of petabytes. So the main focus is mostly for the reads and for those applications which is more they are more into bandwidth intensive, like all the AI and ML. And so we are utilizing the key value over NVMe over Fabric. With comparison that we have with NFS, we would see that we will get into the 140 gigabytes, and we are not maxing out, but the NFS maxing out at 3 clients to 37 7 gigabytes. For the next step for our DSS solution is to add the RDMA extension to the existing S3 protocol that we have. So we also put our DSS as an open source, so everyone can go and check our GitHub, our public GitHub, and use it under your own system. Also, we have this YouTube video that it will show you how to build and deploy the DSS software there. Yeah. So with this, I think we'll.
Thank you so much.
Sure.